2014 Physics Senior External Exam, Paper 1, Part B, Question 2. The graphs below relate to a simple pendulum. Let's just draw a diagram of a pendulum as it swings backwards and forth. So here it is to the left, swings through the rest position, goes out towards the right and swings backwards and forwards. So we can put a mark on here just to show the direction of movement. The first graph represents the pendulum as it moves through various displacements from its equilibrium position. So the rest position here is referred to as the equilibrium position, so we'll call it EP. The second graph represents the interplay between potential and kinetic energy. Now, here in the center, the kinetic energy here is a maximum. As it goes out to each side, the kinetic energy becomes zero because it stops. So here, the potential energy here is maximum. As it goes through its equilibrium position, the potential energy is zero because it's at zero height. So our height is always here through our rest position, and therefore we can measure the height here that the pendulum rises with each swing. So we've read our question. Let's read the graph now. Okay, we've got a positive displacement and we've got a negative displacement. As the displacement here is going through the rest position, swinging out, if we call our right positive and our left negative, let's say, it swings out to the right, goes back to its equilibrium position, swings out to its left, goes back to its equilibrium position, swings out to its right. So you can see how the displacement time graph. With the energy, with the kinetic energy here is at a maximum, and that maximum, if I dot my line up, is as it swings through the rest position. Then the kinetic energy becomes a zero when it stops at its maximum displacement. As it swings back through the rest position, you can see here that its kinetic energy becomes maximum again. Then its kinetic energy becomes zero as it stops. And so the kinetic energy here and the potential energy, basically it's the reverse pattern. As one's maximum, the other's minimum. And then as one becomes minimum, the other becomes maximum. Mark a point on the first graph. So here's our first graph here above. So let's highlight that. Mark a point on our first graph that indicates a time when the pendulum is moving away from the equilibrium position. So it's moving away. It's moving away. We could have those particular points marked there. It's also moving away here, and it's moving away here because it comes from the rest position and moves away. So you can see the arrows there all indicate moving away. So any one of those points labelled an A would be okay for answers to Part A. Part B, draw a line on the second graph representing the total energy. The total energy is just the sum of these. So this here is the total energy. Draw a line on the second graph. So this is our second graph representing the total energy. The total energy is you add those two up to give you here. Add those two up to give you here. You add that one and that one to take you to here. So there's our total energy. Our total energy remains constant. Redraw the second graph on the axis provided in the response book, showing how the graph would develop over time as the pendulum lost energy. Now I'll do this over top of this particular graph. If we're going to lose energy, instead of this orange line here being straight, this orange line here is going to slowly drop off. Alright, so this here is showing it's the loss of energy, and so we need to adjust our lines here. So the wavelength stays the same, and all that happens is instead of going up to the constant total energy, you actually go up to the energy loss line, so that it's slowly going to peter out. So this is still the kinetic energy, and that's the gravitational potential energy, but this total line squeezes down. You must keep the period of the pendulum the same. It's just as it swings, it's just going to get slower and slower, and eventually get shorter and shorter and shorter until it stops.